A very welcome to the Quantum Physics by Quantum Kishan, Quantum Farmer, Quantum Krishak from Bharat. And today we are going to learn about the matter waves and uncertainty principle. In the previous lecture, we have learned how quantum physics emerged in order to explain certain experimental results and natural phenomena which could not be accounted by classical physics. We also studied the concept of wave particle duality and matter waves given by de Broglie. We also explore this concept further in these lectures. Now you know that waves are spread all over space whereas particles are localized. So a single wave would be inadequate for describing a real particle correctly. Then the question is, how do we represent matter waves or wave particles in a space? For this purpose, we have to introduce the concept of a wave packet. The discussion of wave packets leads us to another fundamental principle of quantum physics, namely Heisenberg's uncertainty principle. Now you will study some application of the uncertainty principle, in particular for the microscopic world. The uncertainty principle we met with a great deal of opposition from stalwart in physics, especially from Albert Einstein. The debate amongst physicists and in particular between Bohr and Einstein about the validity of this principle makes a very interesting reading in the history of quantum mechanics. In this unit, we will give a flavor of some ideal thought experiments which provide support for the uncertainty principle and ultimately stated it as one of the fundamental principles of quantum mechanics. So, after studying this lecture, you should be able to explain the concept of a wave packet, derive the relation between phase velocity and particle velocity, apply Heisenberg's uncertainty principle to microscopic system, and discuss the gamma ray microscope, single slit and double slit interference experiments in support of the uncertainty principle. So first see the matter waves. Matter waves. This is the matter waves. We know that classically a particle can be localized at a single point, but a wave cannot. Thus, at least for the microscopic particles for which the wave particle duality is significant, we are forced to abandon the classical description of a particle. We have to look for a new description which should be consistent with the de Broglie hypothesis. What should this new description of matter waves associated with particles be like? Well, for one, matter waves should always be associated with, especially with the particle, in such a manner that the resultant amplitude is non-zero only in the neighborhood of the particles. We have a relation from the de Broglie equation, lambda equals to h by p, so delta lambda equals to del lambda by lambda equals to minus delta p by p. This is equation 1. This equation shows that if delta p equals to 0, then delta lambda equals to 0. That is, we are required to represent a particle of a definite momentum with a single wave of fixed wavelength. However, you know that a wave of single wavelength and frequency is spread out in time and space. Thus, it cannot be localized and cannot represent a particle. Can we find an intermediate solution? If we associate some uncertainty with the momentum, that is, if we take delta p greater than 0, then delta lambda is also finite. The following discussion show that if a finite spread is allowed in the wavelength, we can fruitfully exploit this to represent a microscopic particle. Consider a simple situation in which two sinusoidal waves with slightly different wavelengths are superimposed. For example, suppose we consider two traveling waves represented by psi 1 equals to a sine kx minus omega t and psi 2 equals to a sine k plus dk into x minus omega plus d omega into t. Here, where a is their amplitude and k equals to 2 pi by lambda is the wave number and omega equals to 2 pi nu is the angular frequency. The superposition of the wave else a resultant wave given by psi equals to psi 1 plus psi 2, which comes out to be psi equals to 2 into open bracket cos d k by 2 into x minus d omega by 2 into dt close bracket into sine kx minus omega t. Here we have ignored dk by 2 and d omega by 2 in the sine term as they are infinite small compared to k and omega. And this relation was obtained with using this formula. So here you see, now we can uh, see that psi has an envelope equal to 2a cos dk by 2 into x minus d omega by 2 into t, modulating the sine wave given by sine kx minus omega t. First see the figure. This is the figure 1 showing the superposition of two waves. Similarly, by superimposing a very large number of waves having wavelength close to a central wavelength lambda naught, uh, lambda naught, a wave packet such as shown in figure 2 can be constructed. The superposition of these waves result in a variation in amplitude that defines the shape of the wave packet. The wave packet has regular spacing between successive maxima or minima equal to the central wavelength lambda naught. Thus, the wavelength of wave packet is lambda naught at any instant of time. It is localized in a finite region of space. Clearly, such a wave packet exhibits both wave and particle aspect. Thus, in this new representation, a microscopic particle may be represented by a wave packet. To sum up, we define a wave packet as follows. A wave packet is a group of waves with slightly different wavelengths and frequencies interfering with one another in such a manner that the amplitude of the group is non-zero only in the neighborhood of the particle. The spread of wave packet in wavelength and in frequency depends on the required degree of localization in space and time. We should note that the central wavelength lambda naught is given by the de Broglie relation. So how do we determine the velocity of a wave packet? Clearly, if the velocities of the individual waves being superimposed are the same, the velocity with which the wave packet travels is the common wave velocity. However, in the case of de Broglie waves, the wave velocity varies with wavelength. The individual waves do not travel at the same velocity. Thus, the wave packet has a different velocities from the waves that compose it. Now let us determine the phase velocity v sub p and the group velocity v sub g of the wave packet. We know that the phase velocity vp v sub p of a wave is given by vp equals v sub p equals to omega by k. Hence, from the earlier equation, the phase velocity of the wave packet is given by v sub p equal to omega by k equals to e by p. Now using E equals to m into c square and p equals to mv, in our equation we get v sub p equals to m into c square by mv equals to c square by v. Here v is the particle velocity. Now since v is less than c, it is clear that the phase velocity of a wave packet associated with a particle is greater than that of light. Thus, this should not disturb you because no physical quantity like energy, information, or signal etc. associated with the wave travel with the phase velocity. The quantities move with the group velocity which is given by which is given by group velocity v sub g equals to d omega by dk equals to d by dp, equation 3. Now from the special theory of relativity, we have E square equals to P square into C square plus M naught square into C to the power 4. This is equation 4. And E equals to MC square. This is equation 5 and P equals to MB. This is equation 6. So using this equation, we obtained group velocity as group velocity given by v sub g equals to v. This is equation 7. Thus we see that the group velocity of the wave packet is nothing but the particle velocity, because v is the particle velocity. Thus we have learned that a single wave is not enough to represent a particle. We need to superimpose a group of waves which yields a wave packet traveling at a group velocity equal to the particle velocity. We have seen that there is an uncertainty in delta p in the momentum of the wavelength and a spread delta lambda in its wavelength delta lambda in its wavelength. Before we proceed further to analyze the now we have studied so far in this section that a moving particle must be regarded as a wave packet which satisfies the de Broglie relation. We construct a localized wave packet by superimposed waves, which leads us to uncertainty in its momentum and wavelength. The fact that a moving particle must be represented by a wave packet rather than a localized entity suggests that there is a fundamental limit to the accuracy with which we can measure the particle's position and momentum. For example, The wider the wave packet is, the greater are the number of waves in it, and the better our chances are to determine the particle's wavelength and hence its momentum. But because the particles can be anywhere in the wave packet, we cannot determine its position with precision. If, however, the wave packet is narrow, the particle position is better determined, but now its wavelength or its momentum is difficult to determine. So the smaller is the uncertainty in delta x, that is position, particle's position, the larger becomes the uncertainty delta p in its momentum and vice versa. Thus, we say that a direct consequence of the wave particle duality is the appearance of uncertainties spreads in the momentum and the position of a particle. If one of them becomes definite, the other becomes completely indefinite. This situation is in sharp contrast to that of a classical mechanics, according to which it is possible to determine precisely the position and the momentum of a particle at any time. In 1927, Huygens advanced the above concept in the form of uncertainty principle. So, in the next lecture, we learn about uncertainty principle.